In December 1997, the Galileo probe was preparing for one of the most challenging missions ever undertaken in terms of engineering. The Galileo probe was in orbit around Jupiter, sending us important data about the gas giant. However, this time, the object of study was Jupiter's complicated atmosphere. To obtain crucial data about Jupiter's atmospheric composition, a small probe carried by the Galileo probe was sent to descend into the planet's atmosphere. At 22 hours and 4 minutes on December 7, 1997, the probe made the historic entry into Jupiter's atmosphere, reaching an incredible 15,500 degrees Celsius and losing 80 of the 152 kilograms of its thermal shield. In the first few minutes of the entry, the probe gathered invaluable information about Jupiter's atmosphere, all before it was lost forever. And if a person were in place of the probe, Jupiter is the largest planet in the solar system, both in size and mass, compared to other planets. Jupiter has a mass slightly more than twice that of all the other planets combined. Furthermore, being a gas giant, Jupiter doesn't have a well-defined surface, if it has one at all. To begin the story, we need to choose a height from which we would fall. However, as gas planets don't have a well-defined surface, we usually define our own surface, which is at the height where the pressure is equivalent to 1 atmosphere, the atmospheric pressure of Earth at sea level. Quite intuitive. On Jupiter, this is more or less where the first layers of clouds begin, and the actual fall begins, as Jupiter is much more massive than Earth. This also means that the gravity acceleration is higher, meaning the fall is faster. Now the question is how fast on the surface. We just defined the gravity acceleration is about 2.5 times higher than the gravity acceleration here on Earth. This is enough for you to reach the speed of sound in just 14 seconds. Quite fast. As you fell, you would traverse some cloud layers at the top of Jupiter's atmosphere. However, they are not pleasant at all. The first of them is a layer of ammonia or ammonium clouds. But there's a catch, this ammonia is probably in its solid form. At this point in the fall, you would already be falling at 1,500 meters per second. Imagine one of those blocks of ice hitting you at 1,500 meters per second. That wouldn't be pleasant. After 2 minutes from the start of the fall, you would have already passed the altitude where the Galileo probe, which entered Jupiter's atmosphere, stopped transmitting, 156 kilometers below the defined height 0. Considering that you survived the ice blocks, another very serious problem would threaten your fall: overheating. Contrary to what many people imagine, it's not the friction with gases in the atmosphere that makes meteorites catch fire. It's actually the compression of gases. Whenever you compress a gas, it gains energy and consequently heats up. If you do this too quickly, the gas doesn't have time to lose the energy it just gained. So, what we call adiabatic transformation happens. The gas, in our case, the atmosphere, heats up a lot and incandesces, a fancy word for catching fire. In Jupiter's case, it's not a meteorite, it's you compressing the gases of the atmosphere, and you're the one heating up. So, very likely, after 2 minutes from the start of your fall, you would have already died from overheating. If there were a way not to overheat while falling. Let's suppose that right after the start of the fall, you open your parachute large enough to make you fall very slowly. This way, you would pass through the ammonia clouds, without the risk of being hit by an ice block at 1,500 meters per second, and that's important. Alright, ammonia is corrosive. But let's assume, for the purposes of this video, that you would be wearing a special suit that wouldn't be corroded by ammonia. Even so, you would be far from being safe because Jupiter has very strong winds, and already at the great heights of the ammonia clouds, they can reach 100 meters per second. This is 30 meters per second faster than a hurricane needs to be considered. Category 5. I'm not a parachuting expert, But something tells me that opening a parachute while gusts of wind of 100 meters per second haunt all sides doesn't seem to be a very safe experience. It's getting increasingly difficult to survive in this video. I just wanted to get to the interesting part. Hold on, interesting part. Let's suppose that you survived everything I mentioned so far. Being immersed in a gaseous atmosphere means that you are subject to a force, buoyancy. The entire body immersed in a fluid experiences this force, which is exerted in the opposite direction of the weight force. It pulls upward. It's buoyancy that allows fish to float at a certain depth, not necessarily the bottom of the oceans. It's buoyancy that allows very heavy transatlantic ships to float on the water, even being incredibly heavy. It's buoyancy that makes helium balloons escape from the hands of children at the mall. And it's buoyancy that makes you float on Jupiter. Yes, float on Jupiter, as weight and buoyancy act in opposite directions. This means that the two can cancel each other out, and when that happens, the body floats without any resultant force. But the condition for this to happen is that the density of the body, in this case, the human body, must be equal to the density of the fluid in which the body is immersed, in this case, Jupiter's atmosphere. The density of the human body is about 950 kilograms per cubic meter, which is very close to the density of seawater. That's why humans can float in oceans. If you fell into Jupiter and survived everything, you would fall until the density of the atmosphere was equal to the density of your body. But just for comparison, the density of the atmosphere here on Earth at sea level is 1,000 times lower than the density of the human body. That is, the atmosphere here on Earth would have to become 1,000 times denser for us to float in it like helium balloons. But in terms of atmosphere, we can make an approximation and say that increasing atmospheric density 1,000 times means increasing atmospheric pressure 1,000 times. In the best case, you would be subject to a pressure of 1,000 atmospheres, which is a little less than the pressure at the bottom of the Mariana Trench, the deepest place in the oceans. You would be crushed, and that would be your end. You would be forever floating in the dark, where the rays of sunlight can't reach. But now, you would be forever a part of Jupiter.